All right. Number 21. If an object's acceleration is a at t equals the absolute value of t minus 1, subtract 5, and v at 1 equals 5, find v at 4. All right. Let's go through this, how you would solve it. I think this is going to require a calculator. Yep. All right, so this is going to require a calculator to do. So we're going to set it up, use your calculator, and I'll show you the setup. So my goal is to take this information and to be able to find what the velocity is at 4 seconds. So this is a starting value problem. So the value we're starting with is at 5. And then we're going to integrate from 1 to 4, and we're going to integrate the acceleration. See, the integration of acceleration is velocity. So from 5, add that velocity will give us what we need. And that's it. Let's put it in our calculator. So what would that look like? 5 plus integration so I just went menu, calculus, found integration, from 1 to 4. The absolute value bars, press the number beside the number 9. So to the right of 9, there's a button to press, brings up this screen. Find the absolute value bars, there they are. Press enter, and then square root, so control, and it's the blue there, so control x squared, there it is. I'm going to use t, so t subtract 1, subtract 5. Make sure subtract 5 is outside the square root sign, and then the variable we just used was t. Control enter, and let's make sure that my answer key agrees with me. So 16.535. Perfect. And then the units are feet per second. So you're given acceleration. You're given a starting value for your velocity. So we start with the starting value, add, and we integrate from 1 to 4 the acceleration, use your calculator, and we have our answer. 22. This one's a long question. So we're given a position equation, t cubed. T cubed subtract 3t squared plus 1. And it represents the position moving along the x-axis horizontally. So we're going to start answering the questions that are asked. So can you find the velocity of it? That's actually pretty simple. So it's 3t squared subtract 6t. That's just the derivative. B is also simple. Find the acceleration. That's the derivative of the velocity. That's 6t. Subtract 6. Can you find the velocity of the particle at 1? So just plug 1 into the velocity and then solve it. So it ends up being 3 take away 6. So it's negative 3. It doesn't give you units, so it's just negative 3. D. Find the speed of it at 1. Well, the speed is the absolute value of velocity. So it's the absolute value of negative 3. So let me show you my work. So you're given the position, take the derivative again, plug in 1 into the velocity. Speed is the absolute value, so it's still that answer, negative 3, but the absolute value, which is positive 3. E says at what time is the particle's velocity decreasing? So for that, I need to actually take the acceleration and find the sign. So when is the velocity decreasing? So it's the acceleration that will give me the increasing and decreasing of that. So if I take the acceleration, make it equal to 0, and then solve it. So I'm going to add 6 and divide. So the acceleration equal to 0, add 6, divide. I'm going to draw a number line for acceleration. And then into the acceleration, if you plug in a number smaller than 1, it's negative. Bigger than 1, it's positive. And so when is it decreasing? It's right here. So from 1 to infinity, the velocity is increasing. Velocity increasing means the same as when is the acceleration positive? F. Find the displacement from 1 to 4. So displacement, all that matters is take the position, plug in 4, plug in 1, and then just subtract them. So plug in 4, and again you're plugging 4 into here. So you can use a calculator. Plug in 4, plug in 1, use your calculator, and then subtract the two answers and you get 18. Now find the total distance from 1 to 4. So to understand the total distance from 1 to 4, is there a time where the object changes direction from 1 to 4? So to understand that, I'm going to take the velocity. Let me take the velocity and make it equal to 0. So take the velocity equal to 0. I'm going to factor out a 3t and see that when t equals 0 and 2, I need to check. So when I draw a number line, I want you to notice that from 0 to 2, if I plugged into the derivative, it would be positive times a negative, and then that. So it actually doesn't matter left of 0. From 1 to 4, at 2, it changes direction. So if I want to find displacement, then I need to go and understand that I need to go 1 to 2. So plug in 2, plug in 1, right? Then add, and it's the absolute value of that. And then add, and it's going to go from 4 to 2. So you'd use your calculator. You'd plug into the position positive 2 and positive 1 and subtract. You plug in positive 4 and positive 2 and subtract. And then whatever answer you come up with, it's the absolute value. So these are positive numbers. So if you did it, the correct answer would be 22. So again, using an understanding that for total distance, we need to know if the object changes direction in the middle of the interval. And it does. At 2, it changes direction. So I got to go from 1 to 2 and 2 to 4 separately. The one from 1 to 2, this one's a negative answer. So the absolute value would change it to positive. This one's already a positive answer, so it'd be fine. All right, H. H says, with your calculator, integrate the velocity from 1 to 4. So integrate, oh no, without a calculator, I'm sorry. So without using a calculator, integrate from 1 to 4. So if I integrate velocity, it's back to position. And then I just plug in what I have. So the position is t cubed subtract 3t squared plus 1. So that's working back, integrating, go back to position. And then I plug in. So then I would plug in 4, and then I would plug in 1 and subtract. And we already did that work for f. right? That's exactly what that is. So it equals 18. So it says, what do you notice? That when you integrate velocity, that's the same as displacement. So integrating the velocity gives you displacement. And then I said, how about that last part, I, what does that give you? Use your calculator. So this one, use your calculator and do the absolute value of that. So now use your calculator and do the absolute value of that and see what answer you get. So let's do that. So I'm going to use my calculator, menu, calculus, integrate. And I'm integrating from 1 to 4. Absolute value. And then plug in the velocity, which is 3t squared, subtract 6t, and then dt. All right, so plug in what the velocity equals, go Control Enter, and what answer do you get? 22. Wait a second, where did I see that number before? So, if I want total distance, instead of this long work with your calculator, you can integrate with the absolute value of velocity, and it will give you total distance. Same thing in terms of understanding displacement. If I just want to find displacement, integrate velocity from 1 to 4, use your calculator, and in one step you can get displacement and you can get total distance with an easy step rather than the long substituting in kind of steps that you have to do up here. So that was the connection. The absolute value of velocity when you integrate gives you total distance. If you just integrate velocity, not absolute value, it gives you displacement. So this one is displacement. This one is total distance. And it's a lot quicker, better way to actually get displacement and total distance if you have a choice. Almost there. So it says that there. Now you have two ways to find displacement and total distance. Using definite integrals, displacement is just velocity with your bounds. Total distance is using the absolute value of that. So given a choice, always do total distance evaluating using a definite integral on your calculator to make it more efficient. Here's another calculator question. Find the area between 2 to the x on the x-axis and that interval, and then show an integral setup and evaluate using a calculator. So to find the area under the curve is integration. We're integrating from 1 to 3, 2 to the x dx, and that's it. Oops, I did that one. So I want to know the area between 1 to 3 for 2 to the x. So this integral setup gives me area under the curve from 1 to 3. Type in using your calculator and you find the area. Menu, calculus, integrate from 1 to 3, 2 to the x, dx, and that's the area, 8.656. No units necessary. All right, last one. 24. I think it's the last one. Yep. Okay, so you're given f at x equals x over x squared plus 1. You're given the first derivative is 1 minus x squared over x squared plus 1 squared. And the second derivative, which is 2x, x squared, subtract 3, again over x squared plus 1 cubed. And then there's a bunch of questions I'm going to answer. So A, without using a calculator, list the domain. So when I look at the denominator, x squared plus 1, it's all real numbers. So x squared plus 1, there's nothing that will make that 0. So that means the domain is all real numbers. List any vertical. We have no vertical asymptotes, no domain restrictions. How about horizontal asymptote? Well, the bottom is more powerful. So whenever the bottom has a bigger degree, the horizontal asymptote is y equals 0. How about intercepts? We only have the intercept from the numerator, 0, 0. So the x in the numerator is 0 is the intercept. If I plug in 0 for x, I get it too. So only 0, 0 is an intercept. And what type of symmetry is it? So for 24, well, we'll look off the graph. It might be an odd symmetry. Okay. So A is done. Let me show you. So the domain, no vertical asymptote. We have a horizontal asymptote at y equals 0. And we have an intercept at 0, 0. All this is pre-calculus. Part B. Find the extrema, just the x values, and the x values of the point of inflection, and then see if you can sketch it. So if I want to find the relative extrema and the point of inflection, look here. There's nothing that makes it undefined because the denominator will always be positive. So the numerator, take 1 minus x squared equal to 0, add x squared, square root it, and we have two values that we're looking at, positive and negative 1. If you take negative a billion and put it in here, you're going to get a negative answer. Plug in 0 and you get a positive answer. Plug in 1 billion again and it's negative. So it changes from negative to positive to negative. So we have a minimum and a maximum. So at negative 1, we have a minimum. And at positive 1, we have a max. Now, if I want to, oops, I didn't mean to put 0 there. To find the y coordinate, you then would go back here. So if I plugged in negative 1, I would get negative a half. That's a minimum. And if I plugged in positive 1, I get positive a half. There's the maximum. So we have negative 1, negative a half, and positive 1, positive a half. All right, next. Part C says the point of inflection. So I'm going to take the numerator and find the 0. So for 2x, we have a critical number at 0. I'll take x squared, subtract 3. If you add 3 and take the square root, positive and negative, there you go. So on your second derivative number line, we have negative root 3, we have 0, and positive root 3. So from 2x, I get 0, and from x squared subtract 3, I get positive and negative root 3. All right, into the second derivative, the denominator will always be positive. So pick like negative 1 billion, and you can see that the answer is going to be positive. Pick negative 1. Try that again. Pick negative 1 billion, and you'd actually get a negative times a positive, which is negative. Pick positive 1, or negative 1, I mean. If you put in negative 1, you get a negative times a negative, which is positive. Plug in positive 1, and you get a positive times a negative. And then plug in positive 1 billion, and again, it's positive. So it alternates back and forth. So that means at negative root 3, there's a point of inflection. At 0, there's a point of inflection. And at positive root 3, there's a point of inflection. So those are the point of inflection. If I go back and try to figure it out, negative root 3, if I square root 3, it's 3. So it's 4. So it's root 3 over 4. So the first one would actually be negative root 3 over 4. And the second one would be positive root 3 over 4. So can you sketch with this information? So that's what I'm going to do right here. Okay, so that's all I need to sketch it. So we have an x-intercept at 0, 0, and a y-intercept. I know the end behavior eventually is 0. So we do have a horizontal asymptote. Notice that x has an odd exponent, so it is going to cross over. At -1, -1/2, we have a minimum. At +1, +1/2, same thing. We have a maximum. Now, where's -√3 and +√3? So it's somewhere between 1 and 2. And √3/4 doesn't quite get up to 1. So like somewhere here, and then somewhere here. Those are going to be my point of inflections. So connect the dots. So we have our end behavior. So first of all, it's concave down, and it's decreasing. And then at -1, it's concave down to here. And then after, from -√3 to 0, it's concave up. So concave down, then concave up, concave down, and then concave up. And then I've connected the graph and the end behavior. So I found in the end behavior 0, all real numbers, no vertical asymptote, y equals 0, 0, 0. We found the minimum, maximum, the points of inflection, the changes if it smiles or frowns, and that's everything. Then it says, hey, check a calculator, see how you did. So I'm going to go to Desmos, and then type it in. I'll show you. So I'm going to type in x over x squared there we go. I'm in the way. So again, x squared plus 1. So there it is. So you can compare what we did. So notice at 0, 0, at 1 and 0.5, at -1 and -0.5. So I can definitely confirm the intercept and the maximum and the minimum. And then somewhere here the concavity changes. But the point of inflections aren't on Desmos, so you can't confirm those. But if you look at our graph, it looks pretty well just like that. We did a good job. All right, I'm proud of you. You are finished. You did your work. And until next time, Mr. G Math, over and out. Good job getting your work done.